Bismillahirrahmanirrahim. So let us start our module 9. In this module, we will be designing the structure walls as per the ACI 318-14. So the first step for the designing of the walls is that the walls must be assigned as pair levels. That you must assign pairs and spandrel levels to the structure walls in order to design those elements. So there is a two terms. The first one is the pair, and the second one is the spandrel. Pair is used for the vertical members, and spandrel is used for the horizontal members. That is normally above the opening of the walls. So this will act like a beam spandrel. So it will transfer the forces to the pairs, and that the pairs will transfer those forces to the foundation. So the pairs level shall be assigned to the vertical elements, and the spandrel shall be assigned to the walls portion that is normally above the opening of the lift walls. So if you don't assign these labels, software won't be able to design these walls for you. So how can you define these labels? You can go to the define, and you can uh, define tab, and in that you can define the pairs, or you can define the spandrels. So if one pair is assigned to all the walls, for example, these are the different pair labels P1, P2, P3. So if you assign, for example, P1 to all the lift walls, for example, lift 1 and lift 2, and also to the shear walls, lift walls and shear walls, and the retaining wall. So the software will display a single value of reinforcement that will represent the reinforcement on all the structure walls. Similarly, for the spindles, if you assign the same spindle S1 to the same spindle beams, so it will show you the single value for reinforcement for all the beams. So how you define this? You can see the pair level has been assigned for this lift is P2, and for that lift is P1. How you can define that? You can go to define and click on the pair labels, and you can define you or by just clicking by write, for example, any name. I want to make it, for example, P 121, and add new name. It will be defined. For example, if you want to uh, define it with, for example, X, you can add X1, add new. So new pairs will be defined, and click OK. Similarly, for the spindle, you can add, for example, V name, add V1, V2, right, and click OK. And then you can select, for example, only this wall. For example, you want to assign, and then you can go to assign shell uh, pair labels, and you can assign the defined pair labels. For example, we have defined x1, you can apply it as it is, right? So it will be x1, that will be p1 and p2. So in normal practice for the lift walls, we have same walls, so we will assign the same pair labels to the lift, and we will different pair labels to the retaining walls. So this is how it will look like when you assign the pair labels in spandrels. For example, this is the actually the in our case there is an opening in the lift. So the lift portion above the opening is S2, and the remaining is P1, and you can see the 3D view that this S2 is actually this one. It is above the opening of the lift wall, and the remaining walls are P1. You can see it in the plane as well. The remaining portion is P1, and the opening above the opening, the wall portion is S2. So it will act as a beam when the demand comes on this beam, so it will transfer into the pair P1, and that P1 will transfer it to the foundation. So let us go to the E tab. I have already assigned different pairs, but I will assign it again. Let me uncheck these floors. We will go to the one plane, and you can see that the pair 3 has been assigned to the retaining walls, P2 has been assigned to the this left 2, and P1 has been assigned to the left 1. So this is how you can assign, and I have showed you that how you can assign. For example, let me select these walls, right, and go to the assign shell pair labels, and you can assign any pair you want to assign to the specific walls, or you want to select all, right. So let me undo this, and I will select the retaining walls only. Go to the properties, wall sections, select retaining walls, and I will go to assign shell pair labels, and it is actually P3. So we will make it as P3 again because it's already P3, but I will just want to show you how you can assign it. Similarly for the P2, you can do that. For the spindle, you have to select the spindle by selecting all stories, and this is actually the opening, and you can select that opening, and you will go to assign shell and click on the spindle labels, and you can assign any spindle uh, label to the name. For example, if I hide these spindle, you can see that there is an opening which is shown in the architecture drawings. We show all objects. So this is how you can assign the pair label, and it is very important before designing the walls. So after assigning the pair labels, the next step is to select the design code, and then you have to start the designing. So before that, let us check the minimum reinforcement table as per the ACI 318-14. And it is defined in the table 11.6.1 that when the in-plane shear capacity of the concrete is greater than the demand, this table is followed. For example, a 0.55 VC is actually the shear capacity of the concrete. So if this capacity is equal to or greater than the VU, which is the shear demand, so this table will be followed, and in our case it is cast in place deformed bars. So if the bar size you are using is less than or equal to number 5, and Fy is greater than or equal to grade 60 steel, the minimum longitudinal reinforcement ratio is 0.0012, and for the transverse is 0.002. When the Fy is less than 60, 0.0015 and 0.0025 will be followed. If the bar size yours, for example, you are using number 6 bar or number 8 bar, and Fy is undependent, it does not depend on the Fy, you can use grade 60 or grade 40 steel. The ratio for the longitudinal will be 0.0015, and for the transverse will be 0.0025. But most of the time the concrete capacity will not be greater than the demand. So this ratio will always be followed as 0.0025 for the transverse, as well as for the uh, longitudinal reinforcement. And this limit is for both. That, for example, the in plane VU is greater than, which means the shear demand on the walls is greater than the shear uh, half of the concrete capacity, then these A and B shall be followed, and normally this PT, which is the ratio of the uh, reinforcement, it is 0.0025. So normally this will be followed, and you will see that in the E-tabs it also takes this ratio. This ratio is taken in very rare cases where you have very small building, for example 2-story or 3-story, and it is not in the very high seismic zone, then this table can be followed. Otherwise, in most of the cases you will follow this ratio. So for the designing, you will go to the design and click on the share wall design, and click on the view revised preferences, where you can select the design code, whether it is ACI 318-14, whether it is 11 or any other European code, Hong Kong code, you can select that code. And from here, you can select the rebar material, whether it is grade 60 or whether it is grade 40, and keep the remaining factors as default. After that, you will go to the again design, share wall design, and then you have to start design slash check, and it will start the design of the walls. For example, let's click on this, so it will start the designing of the RC wall. So when it finished the designing, it will directly show the longitudinal reinforcement in the pair wall pairs of the RC walls. And then you can right click on it and you can check the different properties and reinforcement in the you can see there is nothing, but if you move the cursor over here, it will show a value because it is a single value. If you go to the 3D, so it will give you the reinforcement in the longitudinal reinforcement in this number form, and it gives me 186.2. This is actually the reinforcement of the retaining wall because we have given the pair level as one level for all the walls, so it will show me the value at the center, which is this one. If you right click on this in any of the wall, it will give you a report about this shear wall design, that what are the different parameters, what are the material properties used, and what is the reinforcement ratio. And you can see that the required reinforcement ratio is 0.0025, and this is the total reinforcement required as per this ratio. You can calculate this reinforcement by yourself. You can if you have the total length, which is the 6,240 inches, and the thickness of the wall is 12 inches, right? So let me show you the thickness, how the software calculated the total reinforcement. So you multiply 0.0025 into thickness of the wall and into total length of the wall, which is the 6240, 0.0025 12 and into 6240. So you can see that it is 187.2, which is written in here, 187.2. And this is how you can calculate the total reinforcement required, and from the total reinforcement you can find out the ratio of the reinforcement. So this is the flexure design for the retaining walls. Yeah, the total reinforcement required is this, and the ratio used by the software is this. And we verified that how this 187.2 is calculated by the E-tab by multiplying the uh, reinforcement ratio into the thickness and into the total length. Uh, Same for the shear design of the walls, that the rebar required for this is 0.36 inch square per foot, right? You can also calculate for the flexure in terms of the inch square per foot by multiplying 187.2 by 6240, and you will see that it will also give you 0.36 because both of the design flexure and shear has been designed for the minimum, and the ratio is used is 0.0025, which I have explained in here that mostly this ratio will be followed. So let me calculate the reinforcement ratio of reinforcement in inch square per foot for the flexure in order to verify that this thing 0.36 is from the 0.0025 ratio. And how we calculate that, you can multiply 0.0025 into, which is the minimum reinforcement ratio, into 12 thickness of the wall, and into 12 to convert the feet into inches, and it comes out to be 0.36, which is written in here is 0.36 inch square per foot, it means that the software has designed our structure on the minimum reinforcement as per the code. We can also calculate the inch square per foot for the flexure as well by using these values. For example, 187.2 187.2 divided by the total length, which is 6240, right? This is inch square per inch. So you have to convert this into the feet. So you have to multiply with 12, and you can see that the for the flexure it's also 0.36 inch square per foot, same as we have in our shear wall. So for the both it is 0.36 inch square per foot calculated from the minimum reinforcement required. So for the retaining wall in the ETABS results, the ratio is 0.0025 and the bar area is 187.2, right? So this is actually the total reinforcement required, and if you want to give the reinforcement in one layer or in two layer, it's your choice. So you can calculate that as I have explained, and it is 0.36 inch square for one layer. So we will use two layers, so we have to divide this reinforcement by 2. So it is 0.18 inch square per foot. So using number 6 bar, using number 3 bar. So using number 3 bar, the area of bar for number 3 is 0.11 divided by 0.18 into 12. So it is 7.3 inch center. So we will use number 3 bar in two layers at the rate 6 inches center, because it is a single basement, so there is no such demand on this. So the longitudinal reinforcement is number 3 at the rate 6 inches center in two layers. For the shear it is 0.36 inch square, again same as flexure, so we will use it in two layers. So again the reinforcement is comes out to be number 3 at the rate 7, so we will use number 3 at the rate 6 inches center in two layers. So this was the whole story about the design of the retaining wall. Let me explain some of the design information. You can check in the, this is actually model 2, this is model 1. You can check the going to display design, shear wall design, and you can check on the display design information. So the information display on first was the pair longitudinal reinforcement. You can check the pair longitudinal reinforcement, you can check the pair reinforcement ratio. If you right click on this, you can check the ratio that has been used in the design of the retaining wall, and it will be written in the middle, which is 0.0025. And you can check it out the pair demand to capacity ratio. It will not be available, it is will be 0. Normally it is will be equal to 0, because this ratio, this thing is used when you define your own section in the section designer, and then you can check it out the demand to capacity ratio. You can check it out the pair shear reinforcement, you can check it out the spindle shear reinforcement, you can check it out any failure in your structure, and you can identify all failures in your structure. So, and this is the design input, for example, which material is used. It will give you information about that, and the pair section information, that which section was used in the design of the RC walls. So this was the whole story about the design of the retaining walls. Let us move towards the design of the lift walls, and we will directly go to the E tab. And similarly, similar to the retaining walls, we will take the reinforcement ratio. In case of the lift walls, The enforcement ratio used by the E-type is 0.006. I have taken the maximum value, and if you multiply this with 12 in the thickness of the wall and into convert the inches into the feet into inches, then this inches into feet, then this becomes 0.864 inch square per foot for one layer. And if you want to use it in two layers, so you have to divide it by 2, and it is 0.432 inch square per foot. And using number 4 bar, so it comes out to be number 4 at the rate 5.5 inches, and you center in two layers, and this will be from foundation to fourth floor. Let us check that. We'll go to the design, shade, wall design, to the display, and show me the flexure longitudinal reinforcement. You can check that the value is very high in the low stories, for example 19, 16, 39, 14, 23, and then after that it becomes a very constant. So that's why we have uh, keep that in as 14 inches in the different levels. For example, this is story 1, 2, 3, and 4. So that's why from foundation to fourth floor, we will be using different reinforcement, and after that from the fifth to top we will be using different reinforcement in the lift walls. If I right click on this wall, you can see, so it's keep changing because I have changed some ratio. So the ratio in the flexure is 0.007 at the top and bottom. These are actually the station of the wall. For example, you can see the wall you have selected is highlighted. So the highlight in the highlighted portion, the lower portion of this wall segment that we have selected is named as bottom, and the top is named as top station. So these are the station. This is not the top and bottom reinforcement. This is actually station. So the required rebar area is 14.4 and top, and the bottom is 39.03. So you cannot take these two because you have to take the higher one, and the ratio used is 0.007. So we will update that the ratio is 0.007, and then you have to calculate recalculate all of these, and we will use the ratio of the 7 into 12 into 12 is 1.008, and you have to divide this 1.008 by 2. So we divide this by 2, it is 0.504. So now using number 4 bar, 504, so zero point 0.2 divided by 0.504 into 12, so it is 4.7. It means you can use the number 4 bar at the rate 4.5 inches center to center. This is from foundation to fourth floor. For the shear, it is OX, which is over stress, and you can see in the shear design that it will give you the indication in the rebar that it is over stress. And we've opened this for this wall, and you can see that there is an OS. OS means it is over stress. It means that the section that we have used, or the FC prime that we have used, is not that it cannot be fulfill the requirement or the demand. So you can either increase the FC prime from 5,000 to 7,000 or 8,000, but it will not be economical, that we have to increase the thickness. Because if you increase the FC prime, then the FC prime in the walls or the columns will be different. It will be very difficult in the field to execute these. So in case of increasing the FC prime, we will increase the thickness, but sometime you will be restricted not to increase the thickness from the architect. Then you have to play with the FC prime. So we do not have any restrictions right now, so we will increase the thickness of the wall. Previously we used number the thickness of the wall was 12 inches. Now we will increase the thickness to 15 inches. So after increasing the thickness to 15 inches, the ratio remains the same. For example, it is 0.007. You can check it out in the model. We will also check that. So, but the reinforcement will increase because the thickness of the wall is increased. It is from it previously it was 0.007 into 12. Now this time it will be 0.007 into 15. So it will be 0.007 into 15 and into 12. So it is 1.26. So now you can see from increasing the thickness, it's also increased the required reinforcement. So now we will divide it by 2. So we will get in 2 layers. It is 1.62 divided by 2.63. Using number 6 bar uh, in 2 layers, you can get the spacing is as per the requirement, 0.4 divided by 0.63 into 12. So this is 8.3. So we will 8 is 8 inches and its center. And this is again from foundation to fourth floor. For the shear, we will check it out in this. This is actually version 2, which I've increased the thickness. If I click on this actually, you can see the thickness has been increased to 15 inches. And in the shear, you can see there is no indication of the failure. You can change the thickness, as I assume that you already know that we have to go to the defined section properties wall sections. I have done that because it will save our time. So this is the lift walls, and you can increase the thickness from 12 to 11 inches. If I show you in the modified model that I have already increased the thickness of the wall to 15 inches, this is the lift wall. You can see that the thickness is 15 inches. So right click on this, and you can see that the reinforcement ratio used in this with the increase of 15 inches is 0.006, and we have used 0.007. It is also fine. You can use 0.007 and you can use 0.006, but we will modify as per the tab results, because it has reduced the ratio because we have increased the thickness. And for the shear design, you can check it out. This is the minimum, and in it the bottom it requires 1.32, and we have taken the maximum value, right? So in this way you can check it out the design. You will check the shear design. You can check the. So we'll undo this. For example, it was already in 1006 because it hasn't changed the 1006. So in the shear, we have selected the maximum value, which is 1.32. Because you cannot take this, it will become very difficult for you to use this ratio in the top and this ratio in the bottom. but you have to make it consistent, and you will take the maximum value from the list. So we have taken the maximum value from the list, and it is 1.32, and in using two layers it is 0.36, and using number 5 bars, the area of number 5 bar is 0.3, and if you do that it comes out to 5.4. So we will use number 5 bar at the rate 5 inches center in two layers, and this will be from foundation to fourth floor. The next will be from the fifth floor, to top floor, and from for that the tab has used 0.0025 ratio. If you go to the fifth floor, this is fifth floor, you can see that the flexure ratio that is used by the E-type is 0.0025, and the area required is 17. Similarly, for the share, it has used 0.45 in many of the stations, but in one bottom it is used 0.48. So we will use that, although there will be not significant change if you use 0.45 or 0.48, because it's almost very the values are very nearest to each other. But for the convenient, you will use the 0.48. So we'll use 0.488. Let us do that. And if we divide this by 2, 0.488 divided by 2, 0.4244, and by using number 3 bar, you can use number 4 bar, you can use number 3 bar. So if you use number 3 bar, it will be 244, and let us calculate that. 0.11 divided by 0.244 and multiply with 12, so it is 5.4. You can see that it was previously it was 5.8 and now it is 5.4, which I have told you there will be no significant change. It's a big small change, and it is 5.4, and we have used the share as number 3 bar at the rate 5 inches center in two layers, and we have taken the value from here because the 0.488 was not visible in here. So that's sometimes I do the calculation in the background, but I leave some calculation to do it in the class as well. So this will be from fifth to top floor. So in the summary, for the retaining wall, we have the longitudinal reinforcement number 3 at the rate 6 inch center, and share number 3 at the rate 6. These are the same. For the lift walls, we will be using number 6 bar at the rate 9 inch center from foundation to fourth floor, and for the share we will be using number 5 at the rate 5 inches center. And for the fifth floor, you can see that I have explained that or not, because the ratio was used for 0.0025, and the thickness is 15 inches, and this is for the conversion to feet. And for the two layers it is 0.255. By using number 4 bar, it comes out to be 10 inches, but we will use number at the rate 9 inches. So from the fifth to top, it is number 4 at the rate 9, and for the share, it is number 3 at the rate 5. So you can see there is a consistency in the design, that you have used longitudinal reinforcement at the rate 9 inch center. So at the top, it should be the bar size should be different, but the spacing should be the same, because it is 9 inch center. It is again 9. The bar size is only changed. Similarly for the share, but the share is not an issue. You can use different spacing. For example, this is now 6 inches, you can use this is 3 inches. But this is the issue, because it will be very difficult for the field engineer to execute that. If you are using a number 6 at the rate, for example, 6 inches center to center, and at the top you are using number 4 at the rate 9, so there will be lapping issue, and he will make it different hooks. So to make it easy for the field engineer, try to use different bar sizes, but the spacing should be, it remains the same. There is also a check of the maximum spacing of the walls as per the section 11.7.2. That these checks are the 3H and 18 inches, and this check, the third check, is normally not governing, because it is LW by 3. It's very high, so we don't take these normally. We'll check these two, 3H and 18 inches. So 3 multiplied by the thickness of the wall 15 inches, it comes up to be 45 inches or 18 inches. So this is the governing. Let me make it red. And similarly, again for the transverse reinforcement, it is 3H and 18 inches, and it is also governing 18 inches. So the spacing in the transverse elevation should not be greater than 18 inches and 18 inches. And what we have provided is 6 inches, 9 inches, 5 inches, and 5 inches, which is not greater than the limitation as per the code. So this was the whole story about the design of the structure walls. So if you have any questions, you can ask.